to our last talk by Jacob Tsimerman, who will speak about the Diophantine results in Shimura Varieties.
Thank you very much. It's a great pleasure to be here, and it was lovely to hear all the talks before. I really appreciate the opportunity. I want to speak today about some results in arithmetic geometry. Everything I say, as far as new work I'm going to talk about, is joined with Ben Bakker and Ananth Shankar. I write A-N here to separate him from Arul Shankar, who is also an A Shankar, in case that comes up. And just to set the scene sort of very generally, what is the context for everything we're going to talk about? The context is some sort of family of conjectures that allow you, or should allow you, to deduce arithmetic properties about rational points on varieties from their geometric properties. Sort of many big conjectures that one could say. I'm going to pick the following as sort of the flagship one, sort of what everything's about. Or if you can prove this, then a lot of people will be very happy. If you take a variety x over q, and let's say you make it smooth and projective, and you assume that if you look at the complex points of your variety, and you look at the sort of analytic space here, just the usual analytic topology, assume this is hyperbolic, and I'll say what hyperbolic could mean in a second. Then x has finitely many rational points. So that's sort of the big holy grail of the kind of thing in arithmetic geometry that I want to talk about. And what does hyperbolic mean? Well, one thing you could say is what's called Kobayashi hyperbolic, which means no non-constant maps from the complex numbers, no holomorphic maps that are not constant. That should imply this. And this could be a hard property to get a handle on at the time. So there's various differential geometric things that imply this. So one easy one is you could require, for example, that omega 1x, the sheaf of one forms, is ample. The vector bundle of one forms is ample as a vector bundle on x, which means various interpretations, you basically have enough differential forms to make things of negative curvature that you can use to prove this. So there's various forms of hyperbolicity, but the point is if you're hyperbolic in any serious way, you should get this finiteness statement. I should mention that usually people write a Bombieri-Lang conjecture about things of general type. I prefer this one for two reasons. I think one is it highlights a connection with differential geometry better, and the other is Lang actually conjectured the statement, as opposed to the Bombieri-Lang conjecture, which is a much more uncertain status. Okay, so that's very hard, but let's just talk about the dimension 1 case for a second. So, first of all, if x is a smooth projective curve, you can take x to be genus at least 2, and then this is, of course, the Mordell conjecture. Proved by faulting. Now, if x is compact, as we've been assuming, then studying rational points is the same as studying integer points by the valuative criteria. It's the same as studying, the slightly more general points in z adjoint 1 over n for some n. If x is not compact, then this is not true anymore. And so the sort of morally correct thing to do in analogy with this conjecture is to look at the geometry of your non-compact thing and relate it to integer points and ask finiteness questions about that. Because the rational points sort of won't change under a compactification, whereas the integer points would. And there's many theorems here. There's the Birch-Merriman theorem, Ziegel's theorem, in terms of like affine curves or curves over z and integer points. I want to just mention a recent theorem of Janbazi and Sajadi, which sort of generalizes and summarizes the result for curves, which is if you take a smooth, proper curve over some z adjoint 1 over n, and you look at divisors of degree n, on C, which are a tau over z adjoined 1 over n, which you can think of as saying, look at collections of little n points, which are Galois stable, whose reductions mod every prime away from n are still different. There's no sort of intersections that shouldn't happen primes away from n. Then this is not a finite set. However, if you look at the set mod automorphisms of this curve, this is finite.
What have you written there? Is the div of what?
So div n
Yeah.
of your curve, and this is just et for a tau.
Oita.
Yeah. And this includes all the finiteness statements, that the major ones for curves, as well as the Mordell conjecture. So it's a really nice sort of unification in dimension
Is
1.
proper somehow how it embeds into projective space? What does proper mean?
Oh, sorry. In this, I apologize. It's a habit. In this case, it's the same as projective. In general, proper just means sort of compact. Yeah.
Okay.
But yes. Thank you. Okay. So in dimension bigger than 1, this is sort of way too hard in general. Even for dimension 2, we can't really say anything, but sort of the main example of these hyperbolic things, or one of the main example of these hyperbolic things, is moduli of varieties with some sort of varying cohomology. Any kind of situation like that, then you have some sort of natural hyperbolicity coming from the Hodge structure, so it provides a natural place to ask for these kind of finiteness statements. So one of the main examples of this, and one of the main things I want to talk about, and generalize to some extent, is Abelian varieties. So let AG be the moduli space of principally polarized Abelian varieties. Varieties, which I'm just going to call PPAV. So it's technically a stack, but I'm not going to worry about any of those issues for the start. Some sort of variety, and A1 is the familiar modular curve. So the point set of A1 can be identified with the upper half plane mod SL2Z. And in general, you have some similar description. Instead of the upper half plane, you look at the Z-Go upper half space. And instead of SL2Z, you mod out by the symplectic group, SP2GZ. And the nice thing about this space is that it's a moduli space of varieties, so rational points on it have a moduli interpretation. We're looking at Abelian varieties. And also because, sorry, this is nonsense. And because it's a quotient of a Hermitian symmetric space, it inherits sort of basically all the negatively curved hyperbolic properties that you could want. So it's a very natural setting to study these kinds of questions. So in this case, we have a theorem of faultings, sort of a collection of theorems of faultings. So first of all, just in line with length conjecture, AG is not compact. So to honor that, let's let X in AG, let's say over Q, be some compact subvariety. The complex points are compact, or proper. Then the number of rational points of X is in fact finite. And this in fact follows from the stronger theorem that if we just look at AG and we look at integral points, then this is also finite. Which sort of implies this result immediately. And another way of saying this is that there's sort of finitely many abelian varieties, principally polarized abelian varieties of dimension G over Q, and extending to a point of Z adjoined 1 over n sort of means with good reduction outside n. All primes multiplied n. So we sort of have the finiteness theorem that we want in this setup. Okay, so I'd like to switch to a perspective now, which is the following. We're going to switch from spec Z, or spec Z adjoined 1 over n, to a curve C over some field. We'll vary the field. C is some curve. We're going to treat the integers as a curve in sort of a, in a familiar way. And in line with this analogy, these two should behave similarly. You know, if you look at Z adjoined 1 over n points of some space X, this should be analogous to sort of maps from C to X, genuine maps. And if you look at rational points of this X, this should be analogous to sort of rational maps from C to X, or maps defined on some open set of C. And we want to understand the sort of behavior in this sense. So instead of probing rational points on X, we're going to probe maps from curves. Sort of is a theory which developed simultaneously, and you expect similar behavior. So first let me describe the situation over the complex numbers. So let's say we have a complex curve, and we want to understand, say, maps into AG. And we want to give some sort of finiteness statement or something. So the first observation is that finiteness can't hold. Finiteness of maps into AG fails for sort of a very simple reason, because you have AG1 cross AG2 sitting inside AG, or whatever. It's not quite an injection, but more speaking, you have the Abelian variety dimensions G1 and G2, and you can just multiply them, which means that you can just vary this factor, right? You can look at like a point constant map cross some sort of map phi of your curve into AG, and this point can vary, and you get a family of maps. So generic, naive finiteness sort of fails. And this isn't actually the only thing you can do. Even if you insist on, well, let me insist on maps which don't factor like this, or in other words, Abelian varieties which are indecomposable up to isogeny, they have no sub-Abelian sub-varieties. Even then, you can still have some other more complicated Shimura stuff going on. Nonetheless, there's a theorem of Abelian, which tells you that if you have this kind of curve C, then if you look at maps from C into AG, this is finite up to sort of this kind of thing, up to flat deformation. And so, in particular, this implies that the set of possible maps from the pi 1 of your curve into SP2GZ, which you would get from such a map, mod conjugacy is finite. You still get some sort of boundedness for the set of maps, even though you can't expect finiteness because you have some sort of infinity baked into this field. Okay, so the first question I want to ask is what happens.
It's not so clear to me why that is equivalent.
I'm sorry?
Why, I mean,
What is this
it
equivalence
a
here?
priori clear that every homomorphism is realized by a map from C to AG?
Why?
No, I'm asking. So you're saying these?
No,
you say
sorry. I'm
IE
saying that the set of these homomorphisms, which are realized by maps from C to AG,
Oh, I see.
up to conjugacy, because this map is only defined up to conjugacy, is a finite set. No. The group theoretic set morphisms are infinite for sure. Yeah. Mm-hmm. Yeah. Okay. So now let's investigate the question over finite field, which is sort of the usual analog of Z or rings of integers, or sort of curves over finite fields. What do we expect to happen here? Well, here we again have to be careful, just like we were in this situation, because given a map from C to AG, let's call it T, what we can do is we can look at the map from C to itself, given by taking some power of Robinius, which always exists mod P. You could compose that with the map phi into AG. So you get sort of infinite family of maps for kind of silly reasons. And once again, you can't just sort of mod out by Frobenius in the naive way, because you could have this product situation where you only apply Frobenius to one of the factors as opposed to both of the factors, and even more general sort of things can happen. So in this case, we have the following theorem. This is together with Bakker and Shankar from the sort of penthouse suite they have over there. So there's two versions of this. The first theorem is K is a finite field. Let's take K a finite field. So in this situation, the statement is the following. If you look at maps of varieties from C to AG over K, and you quotient out by P power isogenes, means you mod out by sort of a P power torsion subgroup inside your Abelian variety, of which Robinius is an example, because you're modding out by something in the connected part of your Abelian variety. This is a finite set. Okay? And this is sort of the best you could hope for, unless you assume some more. So if you restrict to maps sort of having maximal monodromy, which you can interpret as like, if you take some prime L away from P, then your monodromy is the risky dense in the symplectic group or something, then modding out by Frobenius, powers of Frobenius are enough. That's all that can happen. But in general, you have to worry about sort of all P power isogenes. And the second statement we have is now we're going to work over K bar, where K is the finite field. So now you can't have finiteness for the same reason as before. You have infinitely many K bar points, even if you have finitely many K points. So we would like to make some sort of flat deformation result, but Shimura varieties mod P don't sort of work as well. So we give a similar kind of statement, which is if you look at maps now into AG mod P power isogeny, this is not finite, but it's a finite type family. Okay, so what do I mean by this? So there exists some B over K bar, which is finite type. So you know, some variety over K bar, and a map C from B cross C into AG, such that for all maps phi, there exists some sort of point of B such that phi is equivalent via a p power isogeny to C sub B. So up to p power isogenies, everything's represented by sort of a quasi-compact family, just like a variety. A non-reducible variety.
What does finite type mean?
Sorry, I just mean a variety. If you, like a non-irreducible variety. So finite type means equivalent to like quasi-compact. They have some finite union of varieties, which suffices to cover all the cases, as opposed to like an infinite union of points or something like that. Yeah. Any other questions about the statement? Yeah.
So is what going on here is essentially this kind of two works over non-necessarily practical field that implies one that is in tables? Or
Two works over what, sorry?
is what happens here is the two works, even if K is not algebraically closed, and then it implies one by looking at K points, or the two results kind of completely separate?
They're very similar, but the proofs are very similar. I don't know of a formal implication from one to the other. You do make minor adjustments in the argument.
It's not that you just generally have this B and then you just apply, B of K, and then if K is finite, B of K is finite, or something like that.
No, because you have to be careful, because the p power isogenies that are allowed in K bar might not be allowed over K, which is kind of a silly issue, but morally speaking, it's the same proof. But the statements, I don't know how to make them formally reduce to each other.
Okay.
Yeah. Mm-hmm. But yes, you're definitely on the right track. Morally speaking, that's what happens. Like 2 should be thought of as a stronger statement, I think. Okay, so this is a result over Abelian varieties, and I just want to mention something sort of related. This issue of Robinius, you have the following theorem. Due to Ananth, although actually now that I think about it, Bjorn told me that maybe it was known before Ananth, and I forgot about that. So Ananth asterisk. It's definitely the paper of his, but maybe it was known before. But anyway, so it says if you have a surface mapping to a curve over FP bar, this is like a family of curves, where C itself is a curve, so the dimension of C is equal to 1, and C is hyperbolic, the genus of C is at least 2. Then if you further assume if phi is non-isotrivial, then Mordell holds. Then phi S has finitely many. Well, I guess I can just. No, I can't. Right. S has finitely many sections. So there's finitely many C points of S in here. But if you're isotrivial, if you're constant, this of course can't be true because you have the sort of constant guys going on. And one way that this is related to that caveat up here is that the way you can think about it is that if S is an isotrivial family over C, then S has a Frobenius going on inside of it. You have a relative Frobenius over C. Whereas if it's not, then you sort of don't. So the failure of the Mordell conjecture already in the function field case, in the isotrivial family, is kind of a harbinger of the need to account for these kind of things happening in characteristic. Okay, so I want to talk about this result, but I also want to generalize it. It's primarily where our interests lay. So I want to generalize it to arbitrary Shimura varieties. So I'm not going to give a detailed introduction to Shimura varieties, although, yes? I'm sorry? Oh, I'm sorry. Isotrivial, one way to think about it is the fibers of this map are all isomorphic over FP bar. It's all sort of the same curve. But it might not be globally trivial because you might have some kind of monodromy. So think of like a family of quadratic twists of elliptic curves, for example. The same elliptic curve that you twisted. That's like y squared equals x cubed plus d. That's isotrivial, but it's not actually trivial, because the fibers become isomorphic over C, but they're in fact different curves over Q. It's a sort of the same phenomena in general. Okay, so let me move to general Shimura varieties. And the sort of mantra of these things, they're sort of a fascinating place to work, I think, because these things have all the good properties that AG have. They're hyperbolic, they're symmetric, and they're so they're hyperbolic, negatively curved, they're symmetric, but they're not modulic. They have sort of all the symmetries you could expect, and you have all the sort of properties you have in AG. You're allowed sort of the analogues of Hecke operators, all the beautiful structure Abelian varieties give you, but they're not, at least known, to be motivic. Means that every great thing they have isn't known to come from an actual family of varieties. And things coming from actual families of varieties sort of makes your life a lot easier. In many ways, it makes it much easier to study things. Now, of course, as we'll see in particular in characteristic P or something like that. So it's sort of, working with general Shimura varieties is sort of challenging you if you're in the best possible circumstance. How much can you do without actually having a motivic family? This is why it's
What's the dimension? Is the dimension going to be rather? Are you only going to talk about curves into this, or?
No. Oh, into this? I will talk a little bit about non-curves, but it's mostly about curves.
And what's the dimension of this space? I mean, what are related to it?
Sorry, the space of
The
Shimura.
dimension of the Shimura variety.
Oh, well, I'll say in a second, but I'll be talking about arbitrary Shimura varieties. Yeah, so we will not be restricting to a fixed dimension. Maybe I'm missing the gestalt of your question.
Well, I'm just because I know what the dimension of the other one was. That
Oh, of AG, you mean?
Yeah. So I just want to know something a little bit. But if you tell us about it, go ahead.
I'll tell you something about it, yeah. But if you have your question still, then feel free to ask it again. Okay, so let me give a brief introduction to Shimura varieties, just enough to sort of, make due to what I want to say. So what are they over? Check what the time is. So what are they over C? Well, over C, you do the following thing. You let H be a Hermitian symmetric domain. So there's some classification of Hermitian symmetric domain. There's SP, and there's some other exceptional groups formed. There's some Lie-type classification. Now this has some automorphism group, which is some real semi-simple group. And you let G over Q be an adjoint semi-simple group, such that if you base change to the reals, what you get are the automorphisms of your Hermitian symmetric domain, H. And then what you can do is once you pick a model for G over Z, you can define the complex points of your Shimura variety just to be H mod GZ. So over the complex numbers, this is the kind of thing a Shimura variety is. I'm leaving out a little bit of detail and generality, but this is the kind of space you want to think about. So a priori, this is, it's clearly negatively curved. It inherits the structure of H, but it's not even an algebraic variety. And so then a lot of hard work by a lot of people tells you that in fact things are okay. So we have a theorem due to a bunch of people. So Milne and Borovoy sort of finished it off, and then a lot of the background was done by the groundwork was done by Langland, Shimura, and Abelian. And then the first key step was done by Kashdan, and just the getting an algebraic structure is work of Bailey-Borel, and there's probably others I'm forgetting, but there's sort of a monument of work, which says that this complex manifold acquires a canonical, in some precise sense of the word, algebraic structure of a variety over a canonical number field E, sort of known as the reflex field. So, okay, you have these algebraic varieties, and then they have a lot of very nice properties, but again, we made them sort of in this very ad hoc way, starting from the complex points and then algebraizing and arithmetizing, so nothing lives over them. There's no a priori algebraic varieties that sort of vary over this space. Okay, so what I want to do is I want to state an analog of this Shafarevich theorem we have in characteristic P for Abelian varieties for these Shimura varieties. But the first abstraction there is, well, what do you even mean by that? We have these Shimura varieties defined in characteristic 0, even over a number field, but a priori there's no models for finite fields. And this is partly what I mean by things are much easier when you have moduli spaces, because when we had moduli spaces with Abelian varieties, well, we can define Abelian varieties over arbitrary fields, and so they make sense sort of over Z even. Whereas these guys, you have to work a lot harder to even make sense of what you mean. So, how to get models over finite fields? This is already a very interesting question, and the sort of motivation, we have the following beautiful characteristic 0 result of Borel, which says the following. It's easiest to state if S is compact. So let me state it first in that case. If S is compact, it simply says that if you have a holomorphic map phi from a polydisk to complex points of your space, the analytic points here, then this automatically extends to delta to the n. And then in general, S is not compact. And then you could talk about sort of a canonical compactification, the Bailey-Bragg compactification, but a nicer way, a cleaner way of saying it, I think, is you replace delta star to the n by saying now every map not from delta star to the n, but delta to the n minus the union of all two-dimensional subs of delta to the n minus 2. Every one of these extends. So here we're removing all the codimension 1 hyperplanes, here we're removing all the codimension 2 hyperplanes. So you extend in codimension 2. And if you think about algebra geometrically, it sort of makes sense, right? Because if you have some sort of compactification you're going to extend to that's nice, well, you might map to the rank 1 boundary, that can sort of happen, but you're not going to map to the sort of the boundary in rank 2. It's got to be a divisor. Okay, so motivated by this extension result in characteristic 0, you can, and people have, defined what a model over sort of the ring of integers of a number field should do. So this is a notion of a canonical model formulated by many people. England, Milne, Moonen refined it, and here's a version of it. So we say that S over OEV is a canonical model of S if first of all, it's a model of your Shimura variety. So if you look at the fiber over EV, you just get your Shimura variety back. Second of all, it's smooth. We call it SV, sorry. This is smooth. And third of all, it has this extension property. So for all smooth varieties W over your ring of integers, and all codimension 2 guys, so W prime in the special fiber of W, which are divisors. So W prime here, this is a divisor. So it's a divisor of the special fiber, so it's codimension 1 here, and it's codimension 2 W proper. Every map from W minus W prime to your Shimura variety automatically extends. You don't have to remove the W prime. So this is some sort of like hyperbolicity, but over your ring of integers, some sort of mixed characteristic extension.
So here, the V is given in advance, or is it has to be?
Yes, the phi is the map from here.
No, the V.
Oh, I'm sorry.
The
Yes. For every V, you talk about
want
the
it for
canonical model, and then you can ask if you can give one that works for all V as well.
And you formulated empty special fiber should be okay.
I'm sorry?
And you formulated empty special fiber should be okay, right?
The way I formulated it, the empty special fiber should be okay.
Because
That's-
both set are empty, right?
Yep, that's a solid point. Yeah, right. So this is for what am I missing? You're definitely right. Every smooth guy and every map. Maybe just one non-empty special fiber is the final thing I want. Yeah. Yes. Smooth and not empty. Yeah, smooth and this thing is not empty. Sorry, I'm blanking right now, but it's something like that. Thank you for pointing that out. You're right. Of course. Okay. So that's a canonical model, and it's sort of like in the Abelian type case. So Abelian type loosely means those Shimura varieties you can get out of AG. I mean, there's a lot of details to put in there, but they have some sort of connection to AG. There's some sort of family of Abelian varieties hanging somewhere. And in this case, Kissen and other people sort of constructed canonical models. Basically, whenever they should exist, so at sort of hyper-special level. And then our theorem, oops, right over here, so I have some space. But wait, till when should I go? I didn't really clock when I started, I'm sorry.
About 15 more minutes.
15 more minutes, okay. So that's... So our theorem in this case, it's due to, well, it's our theorem, but it's based heavily on work of Eno and Groshnik, which underlies a lot of the sort of oomph behind us being able to get started, is that in the general case, your S has a model over the ring of integer away from some set of places T, which is canonical everywhere at all the unbelonging to T. So it's I want to emphasize that it's sort of it's an improvement in that it works for arbitrary Shimura varieties, but contrary to the work of Kissen and others, for them the point is they get it at sort of all primes where it's supposed to be true, whereas we get it at some unspecified set of very large primes where a whole bunch of stuff works out for us. So essentially our proof is of the form, take any model and then show that it's canonical almost everywhere, so they exist, and Kissen and friends have to actually make your model at the bad places, which is why it's much harder.
So is a canonical model unique if it
Yes, you can show that it's unique if it exists, just by
So
sort
the
of.
same question for this algebraic structure on S, is it unique?
It's not unique, but it is canonical.
In what sense?
So you don't mean the integral model, you just mean S itself?
Yes.
So I just mean that the machinery gives you an actual variety over your reflex field. Does that answer your question? And which map from Shimura varieties sort of go from one to the other. Am I messing up in some delicate way? No, okay. yeah, but you can twist, and sometimes you can have many other structures as well. It's much fun to get. Essentially, not formally, but basically formally, what happens is you want the structure which is correct at all CM points, and then you show that determines your guy unique. Okay, so once you have these kind of guys, you can now talk about your Shimura variety mod P, and you can try to phrase some sort of Shafarevich conjecture. But one other issue that's missing now is what are your isogenies going to be? For Robinius is always a problem, but the isogenies mod P, if you think about it, are really defined using the moduli interpretation, because Abelian varieties have some notion of isogeny. And so what you do now is you replace them with Hecke operators. So as a simple case, if you take a G inside your Q group, the Q rational G, and you look at the set, the graph Z comma GZ, which sort of makes sense on your Hermitian domain, and then you project it down to your Shimura variety squared. It turns out that the image of this is going to be some algebraic correspondence, some Hecke correspondence, and so you have a huge family of correspondences, and in fact you can do better, sort of adelically, which I don't want to spend much time on, but you can write your S as H cross the Abels, basically after the phone stuff, modulo the Z hat points, modulo GQ. So then for any adelic element you can play sort of the same game. So in particular, for all G in GQP, you get some canonical correspondence inside S cross S. So then what you can do from this guy, in order to get something in characteristic P from something in characteristic 0, you do sort of the bluntest thing possible, because we don't know how to do anything else. You close this up to get something in your canonical model squared, but taking those a risky closure, and then you reduce mod P. And now you can say that two things are isogenous if they're connected by some Hecke correspondence. But as you might expect, you can say something with the extension property, but it's extremely difficult to say anything about how these PGVs actually behave. Right? So we say that Phi1 and Phi2 now maps from some C to SFB are p power isogenous if there exists some G in GQP where the graph of phi1 cross phi2 lands inside PGV. So this sort of very rough operation that we're making. Okay. And then the result is the same one as before. If you look at maps from C to S, I'm going to put a star here to SV, sorry. SFV, so characteristic P maps. Modulo P power isogeny. And then this is finite. And this is over FV. And if you look at maps over FV bar, then modulo P power isogeny. This is not finite, but this is finite. So there's some variety giving everything in the same way as for Abelian varieties. The reason I give an asterisk is this is work in progress, but we can't show it yet. What we can do is we can show this if we restrict to generically ordinary families or maps. So there's some locus here, which is almost always open dense. And if you restrict to maps which are land in that locus or intersect that locus, then we can prove this result. So for Abelian varieties, it literally means you want them to be ordinary and open, and here you have this sort of analog.
What do you assume about the characteristic? Do you assume that what is
Yes, this characteristic is one of the ones for which we have this machinery working.
For which you have a canonical model, or we need more than that?
Oh, you're saying that we formally just need a canonical model?
Yes.
No, we need more. We need more. Yeah, we need. Formally we need we need a bunch of things. Like we need a canonical model for sure. I think the only other thing we need is the Kodaira-Spencer map to be immersive, and we need the sort of magic technology of Eno and Groshnig to apply. So those are two things where we have sort of, in any concrete case, you can sort of run something and get it, but abstractly it's very hard to say which primes work. But yes, we need a bunch of stuff. So there's the star should be removable based on upcoming work of Metapusipera and his collaborators, but at the moment we need the star there. Okay, so let me see something about the proof. If my math was right, I have 5 minutes left, correct? Okay. Sort of what allows you to do this, so very briefly, let's say the proof in the AG case. So usually when I have more time, I present this as like, here is the wrong proof, here is the right proof, but we're going to skip over the wrong proof because we're busy people who don't have time for wrong proofs. Here's the correct one. So the first step is by work, there's a lot of ways to go about this, but Litt has a very nice theorem, Daniel Litt. If you look at the number of QL local systems, on a given curve of rank 2G, arising from an Abelian variety, or principally polarized Abelian variety, this is a finite set. So basically, you just study local systems, you get some basic input from being an Abelian variety, and you can show that, that this is a finite set. So the wrong proof now would be to use Tate's theorem, which is some input you don't have in the Shimura variety case. But even without Tate's theorem, you have a notion of companions, which takes you from QL local systems on your curve. So it turns out that on curves in finite characteristic, if you look at QL local systems as L varies, then they correspond to each other in a really nice way, at least with a few caveats, because essentially they all arise as the cohomology of something geometric, and you just change the coefficients. There's details, but that's sort of the picture. But more useful, it turns out to be to pass to L equals P, which is a harder thing to define, but in this case not so bad. So in this case, it's certain kind of P divisible groups up to isogeny. So if you want, you can sort of tensor with QP formally, or just write this up to isogeny. There's a way to pass back and forth between these, which means by Litt's theorem, the set of possible P divisible groups up to isogeny, now just write tensor QP, arising on C, this is a finite set. So we can restrict to one of them. And so then we can say rho log by passing to an appropriate p power isogeny, because we're allowed p power isogenies, that's in our theorem, we can fix the p divisible group on the curve. And now this is the general game you play in characteristic 0. You sort of keep track of all the L-adic stuff for all L, and then this is how faulting theorems work. You sort of, at the end, you put them all together very carefully, you combine it with some height theorem, and you get a finiteness result. The observation here is that in characteristic P, it turns out you can skip all that because the coefficients at P already record all the necessary information. So it turns out that if you just look at the P torsion, so if you have some Abelian variety over C, what you can do is you can look at the Robinius, which maps from the P torsion to its Robinius twist. And then if you look at the kernel of it, right over here, for a reason we will obvious in a second, this is isomorphic to the pullback along the 0 section of the relative omega 1 of your Abelian variety. Which means if I take the determinant of this, I recover the determinant of this, which is the pullback of the relative omega g in your Abelian variety. And this line bundle over here is pulled back from an ample line bundle on AG.
Kernel of F is a finite group scheme, isn't it?
I'm sorry?
Kernel of F is a finite group scheme.
Kernel of F is a finite group scheme. That's right. So what I mean is like take the bundle defining the finite group scheme over C and take the total space. I mean something like that. Yeah. Mm-hmm. So sorry, I'm skipping a few what isomorphic means. But the point is that this data encodes this data. So once you fix the P torsion, you can actually fix the degree of the Hodge bundle, and that gives you your quasi-compact set. So the observation is like if you can control what happens at P, you can already control the degree of the Hodge bundle, which is enough to give you quasi-compactness. And then if you want to generalize this to Shimura varieties, you replace P divisible groups with F crystals. You sort of try to work with F crystals as best you can. And the hard part of the proof, like the piece that's harder on top of this, I'll just say it in words, is that for Abelian varieties, if I want to modify the P divisible group, like I have something isogynous to this, it's obvious that I can modify the whole Abelian variety via an isogeny to change the P divisible group however I want. Because if I have like a finite kernel, a finite subgroup inside AP infinity, I can just quotient out the whole Abelian variety by it, and no harm, no foul. In Shimura varieties, because these TGs are defined in this sort of very coarse way and have no motivic interpretation, the analog is very difficult. So showing that if you have some sub-F crystal, that you can modify it by doing some global geometric thing like this, because you want the geometric result ultimately, that's kind of the tricky part. Okay, so I'll stop here. Thank you very much for your attention.
Thank you. Questions?
So when you close up the vector correspondence,
Yes.
there is no guarantee that this remains proper in characteristic P, right?
Oh, no, we can show that it remains proper. That's not.
Projection is proper.
I'm sorry.
The projection to the two copies.
It will still be proper. I mean, in the compact case, it's obvious, but you mean in the non-compact case? No, but you can show, at least for the large primes that we're taking, you can show the boundary rolling up to the boundary because you can look at generations of some kind. That's not a problem. Yeah. It of course won't be smooth because it's not even smooth in AG or whatever, or co-dimensional, but it will be proper.
Could you say a little bit more about why once you have the Hodge bundle that tells you there's finitely many choices?
Well, so the Hodge bundle is a pullback of the corresponding bundle on AG. You're looking at maps from C to AG, and it's ample over there. And so if you pull back an ample bundle and you know its degree, there's finitely many varieties inside projective space. Not finitely many, it's a quasi-compact family, a bounded family of varieties of any bounded degree. And so you can just check. So if you want points over a finite field, it's obviously finite. Then if you want the quasi-compactness, you sort of get it from this. Mm-hmm.
Is the work of Noah and Gersony you are using, is it about rigid local systems?
Yes, that's right. To get the crystallinity.
And do you have to apply this work? Do you have to make any assumption about the reductive group you start with?
You mean this rank 2 thing?
Yes.
No, because you can play this is already in another paper, you can play the usual game of if Margulis doesn't, it's a school by dichotomy where take a Shimura variety. If Margulis doesn't apply, that means you're Abelian type. And when you're Abelian type, you already know all the crystallinity stuff because you literally have families of Abelian varieties sitting over you. So in that case, it's easier. So there's this really magical coincidence that Shimura varieties are either Abelian type, because Abelian variety thing, or they're rigid, in which case, you have all these nice other techniques you can apply.
Okay, thank you very much. Thank you all for attending.